So what is our second derivative used for? Well, when we're talking about the graph, the picture, it's concavity. So the second derivative measures the change in the slope with respect to x. Because essentially you're finding the change in the first derivative, and the first derivative measured the slope. That is the concavity of a curve. If that second derivative is greater than 0, then we must have something that is concave up. I can illustrate that with, say, the parabola here. It's concave up. It starts with quite a steep negative slope, but then as we move from left to right, it's getting less steep, and then eventually it gets to 0, and now it becomes positive. So that derivative, if you like, is increasing. It's got a positive change. Concave down then is when that second derivative would be less than 0. Well, what happens in between? In between we have a possible point of inflection. May not necessarily be one, more on that later. This time we're going to just draw a sketch by only using the second derivative. Yesterday we did it by only using the first derivative. Well, we need to find it, of course. There's our first derivative, there's our second derivative. Now this time, what do I know? Well, I know about concave up, concave down. I'll investigate when's it concave up. When is that greater than 0? It's a simple little inequation to solve. It's simply when x is greater than -5/3. Well, there's x is -5/3, so at that point I know it changes to concave up. A very, very rough sketch. It'll look something like that. So it's concave down, then it'll change to concave up. But the beauty becomes when we actually combine the two together. So rather than just using the first derivative or just using the second derivative, well, let's use both tools. And this is really useful for something like a turning point, because we know all the turning points are stationary points. Then, once we've got those stationary points, we just investigate the concavity and we can tell what type it is. The second derivative being positive, got to be concave up, therefore, where's my stationary point? Here it is down the bottom. It's a minimum turning point. And if it's less than 0, concave down, so here it is at the top, maximum turning point. So combining those two ideas. So if I now had to find the turning points of this particular cubic, alright, I'm going to need both derivatives. Find the tools that we are going to use. There's my first derivative, there's my second derivative. Start off, we've got to locate the stationary points. Again, you write down what you're doing, explain what you're doing. Alright, I'm finding stationary points. I know they're going to occur when the first derivative is equal to 0. Solving that quadratic, I get 2 stationary points. So now, rather than drawing the table of values, mind you can still use the table of values. It would be silly using the table of values for this one because it's very easy equations to differentiate. But if you've got a more involved function, like you might have to use a combination of a product rule and a chain rule just to find the first derivative, it might be easier just to look either side of the first derivative rather than, okay, now let's go and find the second derivative. It just depends on the function. So don't forget about that idea of testing either side. It could save you time. Certainly not in a question like this when it's just a straight polynomial, because now I can just substitute my x value into the second derivative and find the concavity quite quickly. It's -4. That's a negative number, less than 0. I know it's got to be a maximum turning point because concave down, up the top. Sub in the other one, I am expecting it to be a minimum, but let's make sure because we're talking about a polynomial. There it is, a minimum turning point. Okay, and I could go and now draw a nice sketch. Let's go back to these things called inflection points. And there are actually 2 types of inflection points. There are inflection points that are also stationary points, and then there are inflection points that are not stationary points. Basically there's 2 types. How do we work out whether it is? Because remember I said the second derivative meant it was a possible one. Alright, we can locate the possibilities. How do I find out? Well, it's a change in concavity. So again, I could just check and see either side of the point. Let's find the inflection point. It's a cubic. It must have an inflection point. All cubics have inflection points, so it must have one. Dy dx is 12x squared plus 12x. There's my second derivative. The possible inflection point will occur when the second derivative is equal to 0. So solving that second derivative, I get one possibility. Now, as I just said, because it is a cubic, I know it must have one. Because I've only come up with one possibility, it must be an inflection point. But that's not good enough for a proof. All right, let's go and test either side. -1/2, I know at that point it has no concavity. Much like we did with the first derivative test yesterday, I now need something on the negative side, I need something on the positive side, not going past any other possibility. Well, in this case there are no other possibilities, so I can pretty much pick any number I like. On the left hand side I'll choose -1, that gives me -12, okay, it's concave down. 0, nice easy number to substitute in. +12, concave up. That statement there is very important, because that is where you're basically saying, hey, I know this possibility is indeed an inflection point. There is a change in concavity. So yep, I know there's a change in concavity, so yes, it is a point of inflection. The one that is also a stationary point, horizontal point of inflection, also known as, you don't see this term used that much in the two-dimensional graphs, it's probably reserved more for three-dimensional graphs, but also known as saddle points. And the reason it's called saddle points, if you did see one in 3 dimension, it actually looks like a saddle. I suppose if you look at the cubic, you can kind of see, well, it's a horizontal point of inflection. You could imagine someone sitting on that and go, yeah, right, let's ride the cubic. But as I say, in 3 dimensions you'd see it more obviously, but we tend not to use the word saddle points in 2 dimensions, so we just say, oh, well, they're horizontal point of inflections, but they are technically saddle points as well. So they are stationary points. The first derivative is equal to 0. The second derivative is equal to 0 because it is a possible point of inflection. Well, it is a point of inflection, but here's the thing. The third derivative will not equal 0. The third derivative will not equal 0. What is the logic behind that? What would the third derivative measure? If the first derivative measured the change in the y value, the second derivative measured the change in the first derivative, so the change in slope. Well, then logically the third derivative must measure the change in the second derivative, the change in concavity. We want to know, is there a change in concavity? So if I substitute into the third derivative and get a number that's not 0, there must be some change in the second derivative. Change in concavity, it is an inflection point. That means we now have an alternative way of finding inflection points. But again, don't forget about the table of values idea. Because once again, if it is a complicated function to differentiate, you're probably going to save time using the second derivative. But if it is just a simple polynomial or something, the third derivative is going to be more efficient. So yes, we know the possible points of inflection will occur when the second derivative is equal to 0. That is actually the rule. If the first non-zero derivative, so the first time you substitute into a derivative and you get an answer that's not 0, if it's of odd order, so third derivative, fifth derivative, seventh derivative, then it would be a point of inflection. If the first time you get 0 is of even order, then it won't be a point of inflection. It's probably going to be a turning point. So if we go back to our example that we did before, and I now add the next tool, the third derivative, and the third derivative is simply 24 for ours, because we're talking about a cubic, then I'd go, well, when x is -1/2, the third derivative is equal to 24, which is not equal to 0. Okay? Therefore, there is a change in concavity. So again, make sure you write that statement. That's what you're saying. Well, that means there is a change in concavity. So yes, it is an inflection point. Again, saving us time having to draw up table of values and testing points and all that. I can just use the third derivative. Exercise, jolly good fellow.